Hello everyone. Today I want to take a look at our kind of next phase of our work with vectors. We've just finished some of the basics of vectors, scalar products and what that means. And the next step is to really set the stage for being able to work with really situations in 3D space. How lines and planes and points are all related, not just on necessarily a plane but in space. And in order to do that, we want to take a look at how we can think of a line a little bit differently than what you're used to. Of course, every time we think of a line on a Cartesian plane, we can go back to the old-fashioned y equals mx plus b, and that still can work, and we can deal with it in some cases. But moving to 3 dimensions, that kind of falls apart. So some examples I think are going to be the best way to go. Make sure you do read the section and study some of the other examples, and of course some of the terms. And I'll try to point out some of the important things as we go. First of all, we want to be able to write the equation of a line through 2 different points, and they are in space. So they have, instead of just 2 coordinates, there are triples, 2, 7, 1, and -4, 3. We could try to plot those points and see how that would all look, but that could be a little complicated. So let's see how we can write the equation of a line. Well, we want to come up with 3 different forms. And the first of those will be our vector form. Okay, our vector form is basically understanding that a line can be represented by a starting point and some direction. But then that direction needs to be multiplied by some scalar. So it might be 2 of those directions, 1 of the magnitudes of those directions, a half, a third, -5, radical 3. So there's going to be some scalar in this. So I can think of this vector equation as picking one of these 2 points. I'm just going to start with the 2, 7, 1. This is my general point x, y, z in space. It will start with 2, 7, 1. And then I'm going to use lambda. I could use k, any one of a number of common scalars. Now we have to figure out the direction. Well, b to a to b, it doesn't matter. I'll go with a to b. So I can back subtract to get the position vector. -1, that'd be -3. 4 minus 7, -3. 3 minus 1 is 2. So that's our position vector. It's our direction vector. We can also write these in parametric form. Parametric form is just kind of taking each of these individual equations out of the vector form. So it could be kind of a series of equations. X equals 2 minus 3 lambda. Y equals 7 minus 3 lambda. And Z would equal 1 plus 2 lambda. And of course, you can probably guess some problems are designed specifically just to be comfortable with the interplay between these 2 and going back and forth. And then the third would be our Cartesian. Cartesian works perfectly when it's in 2D, but in 3D it looks a little funny. And really what it comes down to is we can take each of these and solve for lambda. And if I solve for lambda, here would be x minus 2 over -3. But that has to equal the other lambda, because it's really the same lambda, y minus 7 over -3. And that would have to be equal to the one involving z, z minus 1 over 2. So there are 3 different ways to represent this line going from point A to point B. And this looks a little different, all right, but it is a Cartesian form. And as I said, we just need to be able to move between these 3 very fluidly. The parametric form, this is kind of one of the biggies. We might be given a problem in this form or in this form, but the parametric form is very common. We might even be given an equation of a line in vector form, but instead of writing these types of values, we could use the I, J, and K along with each of these individual vectors. So you'll see that when you get into the problem set, but that's representing lines. Next thing we want to do is find the equation of a line that goes through a point, but has something to do with another direction or another vector. So in this case, we want to go through a point negative 4, 3, and we want to have direction vector 2i minus j. We don't want you to forget that the 2i minus j is another way to think of a vector. Now, that is a direction. So as a vector, we can think of that simply as 2, negative 1. So for the solution to part A, I can simply start with, this is only 2d, the point, which is negative 3, 4, plus, we just want to have 2, negative 1. Again, I can have k, I can have lambda, u, doesn't matter, but I'll go with lambda. So I'm done. Now, if I really wanted to, I could try to put that in terms of more of a y equals mx plus b. That would be kind of moving it to the Cartesian form and solving for y. That's not a problem. So let's do that in this case and see what it might look like. In Cartesian form, this could be, well, let's go to parametric form first just to practice it. That would be x. Y would be 4 minus lambda. And if I solve them both for lambda, it would be x minus or plus 3 over 2. That would be this in terms of lambda, which is simply 4 minus y. And then, of course, we can go ahead and solve for y. I'm not going to finish it, but we could turn it into a more standard y equals mx plus b format if we would like, because this is in 2 dimensions. For part B, we need to make use of something that I want to talk through for just a minute. But this idea of normal, we hopefully realize that has to do with being perpendicular. So let's just say I have some point out here. And let's just say this is kind of A. And then we have the normal. Okay, in order to be normal, these vectors have to be perpendicular. And because of that, the scalar product must be 0. So if we think of it, that could mean this normal times, or the scalar product of whatever this one would be, okay, from this point to this point, must be 0. Well, looking at that more closely, we could basically have the scalar product between n and p would have to be equal to the scalar product between n and a, where n is your normal vector, p is kind of the point you're wondering about, and a might be the point that you're given. So, having said that, we can simply write the rather simple equation. Here's my normal, 3, 5. Want to the dot product along with my unknown point P would have to equal the normal here we have a dot product of the A that's given, which is negative 3, 4. And then we just have to play around with this thing in order to get a nice format. And that could look a couple different ways, but let's just go a little bit with it. This would be 3x plus 5y equals, it's going to be negative 9 plus 20. So you get this nice form, 3x plus 5y equals 11. Of course, this one is nice Cartesian form, but more of our standard y equals mx plus, or a standard form for our two-dimensional line. We're line in 2 dimensions. Okay. Now, let's jump to this last one. And before we get to it, just a little thoughts process here. If we think of 2 lines on a plane, there are 3 options. Either the lines intersect, could be perpendicular, but that's still intersect. They could be parallel, which means they have no point in common, or of course they could coincide, which means they are the same. Every point's in common, but it's still a relationship between 2 lines. We move to space, we have another option. We could still have parallel lines, we could still have intersecting lines, we could still have coincident lines. But the next option is they could be skew, which means they're not parallel, but they also don't intersect. Sometimes we can even define skew as non-coplanar. They're not even on the same plane. So if you think of two lines that are not on the same plane, you can't put a plane between them, so to speak. They are called skew. So what we want to do is to show that these two lines are skew. Now, that really goes back to what I just mentioned. To be skew, they can't be parallel, but they also can't intersect. There are other ways to show this, but I like to go about it with those two factors because they're rather easy to show. So let's first consider whether or not they're parallel. If we look at these two lines, they're in that Cartesian form. Now we could switch them to any one of these other forms, but for now I'm not going to, because I know that this is basically the direction of line 1. So the direction of line 1 is going to be 2, -2, 4. The direction of line 2 is going to be 2, -1, 3. Okay, this we could call direction 1, this we could call direction 2. Direction 1 is not equal to direction 2, so they're not parallel. So we know very quickly that these two lines are not parallel. Now we have to show that they have no point in common. And one option for that is to put them in parametric form. So let's write these in parametric form. Parametric form, remember we can think of this, I don't know, as like a lambda. We can think of this as mu, very common. So this would be x equals -1 plus 2 lambda. This is going to be line 1. Then y would equal, it would be 1 minus 2 lambda. Again, I'm just setting this equal to lambda. Z would be 1 plus 4 lambda. So that's line 1. Line 2, we can do the same thing with mu. We'd have x equals 1 plus 2 mu. Y would equal -1 minus mu. And then z would equal 4 plus 3 mu. We need to double check that to make sure we've converted correctly from the Cartesian form to the parametric form. Now, basically, it comes down to this. If these are not parallel and they don't intersect, they're skews. So if they do intersect, there must be an x, y, and a z that works for both of these. So now it just comes down to letting these two be equal, these two be equal, and these two be equal. And then solve the system. We have -1 plus 2 lambda equal 1 plus 2 mu. Okay, which is, we also have a 1 minus 2 lambda would equal -1 minus mu. And we could even have a third one, which we'll test here in a minute. But if I solve this system, again, give me a little time here, that's going to be, if we add here 2, we get 2 lambda equals 2 plus 2 mu. So lambda is going to be 1 plus mu. Double check my work, because I'm trying to hurry so this video isn't too long. In this case, I just have -2 lambda equals 2 minus mu. So a couple ways to write that. I could say that that means mu is going to be 2 plus 2 lambda. So I'm just using substitution. So if that's what mu is, we have lambda equals 1 plus 2 lambda. So -3 equals lambda. So if lambda equals -3, these two values should be the same for the x and the y. And then we would have to find mu. And if lambda is -3, mu, it looks like, would be -4. Again, doing it quickly. Didn't work through this before, so hopefully it's all good. So if we go ahead and now put some of these numbers in, -3 for lambda, and -4 from u, we can find out the x, y, and z that goes with each of these. This is -3. It's going to be -6. It looks like x is -7. That's -3. We get 7. If that's -3, we get -12 and 1, -11. Here, if we put a -4 in, we get -7. What we thought. If we put a -4 in, that seems to be a little problem. Thought I used that, but anyway, let's go with that. If I put a -4 in here, get -12, and then we get 8. What we would show is that there's an inconsistency. There might be a lambda and a mu that would work for 2 sets of equations, but not for that third. So basically, there is no point that is common to both of these lines. Now again, there are other ways to go about this. There's a nice example of something very similar in the text with 2 different lines. But that's basically what we have. We can write equations of lines in a couple different ways. And once we go to 3D, all of these look different. This is going to be fundamental to many of the things we'll do as we finish out this unit on vectors. But for now, we're basically maybe trying to find intersections of lines, equations of lines, if lines are skew, if they're parallel, what the normal might be, because that would mean perpendicular. So hope this helps a little bit. We'll definitely talk about this in class or when we meet remotely. But until then, good luck with the problem sets from Chapter 9. If you have any questions, as always, please let me know.